So far in chapter 3, we've been focused on polynomial functions, graphing them, finding their zeros, dividing them, that sort of thing. But today we're going to shift gears and talk about rational functions. Remember, rational functions are the functions that look like a fraction where there is a polynomial in the top and there is a polynomial in the denominator. We know from chapter 2 that rational functions have a restriction on their domain, and we know that the denominator cannot equal 0. That's a restriction on the domain. So there's going to be numbers that we have to throw away. So let's just remind ourselves of what that looks like. So for the domain of this function right here, if we were just reviewing this again from chapter 2, we know that the denominator is not allowed to be equal to 0. So what number can I not plug in there because it would make the denominator 0? 3. So x cannot be equal to 3. So our domain would be from negative infinity to 3, and then from 3 to infinity. Basically saying you can use everything except for the number 3. Does all of this sound familiar? Yes. Okay. The trick is, now sometimes it's not going to be as simple to find just like exactly the number that you see, because this equation right here that's in the denominator, this expression, is not in factored form. Our first instincts, kind of like with polynomials, should be to factor whatever polynomial is in the denominator of the rational function, which is why we talk about polynomials before we talk about rationals. Now this one will factor easily. So if we factor this denominator, what numbers multiply to negative 9 and add to 0?
3.
How about positive 3 and then negative 3, right? This is the difference of two squares, if you recognize that pattern. Now, what two numbers am I not allowed to use here because they would both make the denominator 0? Positive 3 and negative 3, yeah. So my domain this time, when I write it, is a little bit more lengthy because we're saying we can use every number from negative infinity, but just not negative 3 and not 3. Everything else we can use. And again, this gets a little bit more interesting when we look at an example like C, where again, we have a quadratic in the denominator. This quadratic in the denominator is not allowed to be equal to 0. If we tried to factor this, there's no numbers that multiply to positive 9 and add to 0. So my first instinct would be to not take the little shortcut of just factoring and using the opposites, but let's actually set that denominator equal to 0 and solve, which is what we're doing with that shortcut of just factoring and solving. To solve this, we would subtract 9 from both sides and then take the square root. But when I take the square root, two things happen. Number one, I put the plus or minus in front of it. But then my spidey senses should go off because I'm taking the square root of a negative number. What is the square root of negative 9? It is the I. It's 3i because the negative number underneath the square root is an I. Yeah. Spidey senses should go off there. So if we were thinking about a real number line, because rational functions are graphed on a real number line, does an imaginary number appear on a real number line? No. So this rational function, because its only restrictions would be an imaginary number, which is not a part of a real number line, this one actually has a domain of all real numbers. There is not a single number that I can plug in that would make the denominator negative, since I'm squaring whatever number is there. So if, and maybe write a note to yourself here, if you get an imaginary number as your solution, there is not a break in the graph there. It's okay to use the entire number line here because the only breaks, quote, in the graph are at imaginary places. And we don't graph imaginary things yet. You might in college. Now, rational functions have some very interesting behavior. Rational functions are the ones when you graph them, like maybe on Desmos, and you forgot to get out of the denominator, like you're typing 1/2 times x, but you accidentally put the x in the denominator, and the graph like whoop, breaks. That's what rational functions look like. So they have very interesting behaviors at different points on the graph, and we're going to discuss those different behaviors because it's going to allow us to graph the function easier. We're going to look at the behavior of the most basic rational function, which is 1 over x. Now, what number am I not allowed to plug into this function because it's in the denominator? Yeah, what value can I not plug in for x? 1 over 1 is fine. 0. 1 over 0 is not fine. So we're going to have something interesting happen to this graph at the number 0. What we would do is when we look at the behavior at the value 0, we would notice that on the left side of 0, this is 0. Let's go ahead and maybe draw that in. Okay, so boom, 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 boom. The left side of 0, your graph is going to skim very, very close to the number 0, but it's not going to touch it. In this class, well, in the previous class, you may have used limit notation to talk about what's happening next to the vertical asymptotes. In this class, we're going to use what's called arrow notation, so this is closer to what you did in Algebra 2. As x approaches 0 from the left side, that's on the left side of 0, the outputs get closer to negative infinity. The outputs approach negative infinity because our arrow is going down. But if we look at this graph, again getting closer to 0, but on the right side of 0, so this is x approaches 0 from the right, we see that the arrow is going up on the right side, so our outputs are approaching positive infinity. This notation of looking from the left and looking from the right is shown by the little plus or the little minus sign as a superscript, so that's up instead of a subscript, it's a superscript, kind of like an exponent, on the limit notation, the arrow notation, sorry. So these graphs are going to have interesting behaviors near these excluded values because they are mostly vertical asymptotes. We are also going to have interesting behavior as the function gets farther away from the origin. As we get farther away from the origin, we are talking about the end behavior. We are talking about, usually, the horizontal asymptote. So these graphs will have vertical and have horizontal asymptotes. We would say, because this is what the graph looks like, as we approach negative or positive infinity out to the sides, we have the following arrow notation. As x approaches negative infinity, f of x would approach 0 because it's getting closer and closer to 0. As x approaches positive infinity, the function gets close to 0 as well because we're getting close to these end values, which is your end behavior. Now, all of that's fine and well, but if we don't know how to find the values of the vertical asymptotes and find the values of the horizontal asymptotes, we're kind of stuck when it comes to graphing these functions. So on the next page, we're going to go over how to actually find the vertical asymptotes and the holes. Now, the line y equal to a is called a vertical asymptote. I'm going to continue to use orange to talk about vertical asymptotes. I know that that's the color I used for just the domain excluded values on the front page because same vibe. The vertical asymptotes come from any factor remaining in the denominator after you factor it. Okay? Now, there are also something in graphs called the holes of the graph, and I'm going to be using purple to talk about holes today. Holes come from values that cancel out of both the numerator and the denominator. So they would have a common factor in the top and in the bottom. That's what all of the information in the theorem box is saying. I feel like the picture is a little bit easier to see. If we have a rational function, we would need to write it in factored form so that we can see which of those factors might cancel out and which of those factors would remain in the denominator or remain in the numerator. Because the ones that remain in my numerator end up being the zeros of the function. So our first instinct, anytime we see a rational function, is probably that we're going to want to graph it. What? We're going to want to factor it. Because factoring it will allow me to see whether I have a vertical asymptote or a hole at those excluded values in the denominator. For example, we need to factor this denominator. We've technically already done this on the first page. This is the one that we factored already. This is x minus 3, x plus 3. When we see it in factored form, are there any common values, common factors on the top and bottom? Like the same exact parentheses? No. So there are no wholes for this rational function. There are, however, two vertical asymptotes. Because of those two excluded values in my domain remaining in the denominator, we know that there is a vertical asymptote at x equal to both positive and negative 3, because those are the two values that would make my denominator 0. We found this on the first page. Those are the excluded domain values. Now, instead of just saying they're excluded domain values, we're going to name them as vertical asymptotes. Now, if we make this a little bit more complicated, this is the same exact denominator as the first denominator, so we're going to fast forward through the factoring. It's x minus 3, x plus 3. We've already factored this once today. But when you look at the g of x function, what is on both the top and the bottom? X plus 3. We have the same factor on top and bottom. That is a hole in the graph. So we're going to take, if you're following my color scheme, that's purple, and we're going to mark it out. But not aggressively mark it out because we still need to see the number. Just put a slash through it because we see that is a hole. So we know the following. We know that there is a hole in this graph at the value x equal to negative 3. What we would have gotten as the excluded value from that pair, that is now a hole. Bless you. Any factor remaining in the denominator, after we cancel stuff out, when there are no remaining common factors, those are going to be your vertical asymptotes. So we have a vertical asymptote at x equal to 3. So there's only one vertical asymptote because the other one was part of a hole. Both holes and vertical asymptotes are excluded values in the domain. So the domain for this function is still from negative infinity to negative 3 to 3, and 3 to infinity. That part has not changed. It's just that one of them is a vertical asymptote and one of them is a hole. And by hole, I mean like straight up like a gap, like a small, tiny little gap in the function. It's a hole. Now we technically solved this one also in the beginning of class when we took this excluded denominator and we set it equal to 0, right? I'm going to fast forward through these solvings because we already did this. We would get the x is equal to the square root of 3i. Just like on the front, we don't graph vertical asymptotes or holes at imaginary places. So there are no holes and no vertical asymptotes for this particular graph, because the denominator cannot ever be 0. We saw that from the front page. So there's no holes and no vertical asymptotes. Because of the I? Because of the I, correct. So the moment you get an imaginary number when you're doing these kind of things, well, one, check your work, make sure you didn't randomly put an I somewhere, but like it's normal. It's going to have no breaks in the graph, no horizontal asymptotes. What? No vertical asymptotes, no holes. Misspeaking about horizontal asymptotes, let's focus a little bit on horizontal asymptotes. So vertical asymptotes come from things in the denominator. Horizontal asymptotes do not. Horizontal asymptotes are talking about as the line extends from negative infinity to positive infinity. That's a horizontal asymptote, as the x values increase or decrease without bound. Now, there's a very complicated way to find the horizontal asymptotes if you don't know 3 acronyms. The 3 acronyms that help us determine end behavior of rational functions, thus our horizontal asymptotes, are BOBO. My AP Pre-Cal friends, do you remember the other two? Botten and Betsy. Yeah, if you had Miss Howard last year, instead of Botten, she said Batu. Same vibe. It's undefined or no horizontal asymptote. Now, if you notice on Bobo, I put like a 0 as the last letter instead of an O again, because what BOBO means is that the degree of the numerator and the degree of the denominator have the following relationship. It is bigger on bottom. Maybe write that down. Bigger on bottom. When the degree of the numerator is the degree of the denominator, bottom, is bigger than the degree of the numerator, then you automatically know that the horizontal asymptote is 0. No extra work required. BOBO, 0. BOBO, 0. BOBO, 0. Because that's a 0. If the degree of the numerator is bigger, bottom stands for bigger on top. When the degree is bigger on top, there is no horizontal asymptote, and it will have an undefined end behavior. But for us, when we're talking about horizontal asymptote, you say none. So the N stands for none, no horizontal asymptote. Betsy is bottom equal top. Maybe write that down. Bottom equal top. So when the degrees are the same, when the bottom equals the top, what you're going to do to find the horizontal asymptote is you're just going to take the coefficients, C, the leading coefficients of the numerator and the leading coefficient of the denominator, and divide them. That number that we get after we divide them will give you the horizontal asymptote. So finding the horizontal asymptote is actually pretty easy if you know my 3 acronyms, BOBO, BOT, and Betsy. Anytime you're talking about end behavior or horizontal asymptotes, BOBO, BOT, and Betsy, the end. Okay, let's see them in practice. We're going to find the horizontal asymptotes if there is one. Notice that all of these examples are very similar, but they're written in standard form, not factored form, standard form. So for this one, you go back to the original question, not in factored form. And we ask ourselves, is this BOBO, BOTN, or Betsy? What's the degree of the numerator? 1. What's the degree of the denominator? 2. So where is it bigger? Bottom, which means this is a BOBO question, a BOBO function. If this is a BOBO function, what's the horizontal asymptote? 0. We're going to say y equal to 0 because it is an equation of the line y equal to 0. Nice. Easy. Let's try the next one. For the g of x function, what is the degree of the numerator? What's the degree of the denominator? So if they're equal, that's Betsy. Bottom equal top, we do something with the coefficients. What we do with the coefficients to find the horizontal asymptote is we divide the leading coefficient of the numerator. What is the leading coefficient of the numerator? What's the leading coefficient of the denominator? 2. We divide those numbers. So this one is going to have a horizontal asymptote at 2. Which means as we extend out to the ends, it should be getting closer to the number 2. For the h of x function, what is the degree of the numerator?
3.
What's the degree of the denominator?
2.
So where is it bigger?
Top.
Bigger on top, which means we're not going to have a horizontal asymptote. Nice. There will be no particular number that the graph gets close to as we increase or decrease without bound. But a great question you might have is, what actually happens then to the rational function if it doesn't have a horizontal asymptote as you extend to the left and as you extend to the right? That's a great question. It's going to follow the particular behavior of a different function. In fact, if you have a bigger on top specifically by 1, bigger on top by 1, you do not have a horizontal asymptote. You have what's called a slant or oblique asymptote. Oblique. Slant asymptotes. Horizontal asymptotes are flat. Slant asymptotes are slanted. A slant asymptote is found for only functions that are bigger on top by 1. So bottom by 1. The last question on the first page was 3 on top, 2 on bottom. It didn't have a horizontal asymptote, but since it's bigger on top by 1 value, it will have a slant asymptote. The graph of a rational function has a slant asymptote if the degree of the numerator is 1 more than the degree of the denominator, bigger on top by 1. The equation of the slant asymptote can be found by division. Good thing we practiced division a couple days ago. Here's the problem, is that last class we focused a lot on synthetic division. Most of the time you're going to have to find the slant asymptote with long division. There's only very particular questions when synthetic division works. Remember, synthetic only works when the denominator is like x plus or minus some number. If denominator is squared, if the denominator has a coefficient, if there's an extra term in the denominator, we cannot use synthetic division. So we hope that synthetic division works because it's significantly easier. Otherwise, we'd have to use long division. Okay, so let's say we're trying to graph our function, and we realize our function is bigger on top, so it doesn't have a horizontal asymptote, but it's specifically bigger on top by 1, like this one. What's the degree of the numerator? What's the degree of the denominator? This is bigger on top by 1. It will not have a horizontal asymptote, but it will have a slant asymptote. Can I use synthetic division to divide this one? Yes. This is exactly what the denominator should look like. X and then plus or minus a number if I can use synthetic. So we practice our synthetic division like we did last class. We'd put a 3 on the outside and the numbers 1, -4, -5 on the inside. Does this look familiar to us? We bring down, we multiply, we add, multiply on the diagonal, we add. It does not matter that there is a remainder. Last class we were sad when there is a remainder. Today, don't care. We're happy. You know what? It's okay today to put a happy face there. Because the slant asymptote does not care about the remainder. Your slant asymptote only cares, wrong color, only cares about these values. So our slant asymptote for this function is at y equal to the quotient 1x minus 1. Ignore the remainder. Do we see how I got that? Even with long division, ignore the remainder.
So do you have to solve that part? Or can we just stop once we get?
What do you mean?
Do you have to do the -5, -3, or can we just stop at once we get to -1 right there?
Since I don't care about the remainder, yeah. As long as you know it's the remainder, so the last value is the remainder, yeah, you can essentially stop. Because all I want is everything but the remainder. Now, if we were graphing this slant asymptote, we would need to graph this function. This is a linear function. What is the slope of this function? 1. So rise 1, run 1. What's the y-intercept? So if I was asking you to graph the rational function, you would have to graph this linear function to act as my slant asymptote. What it would do is it would look like this across your graph. We would have this slant asymptote where the line is going to get close to it but never cross it. So when we put this all together, your job by the end of today is going to be, I need you to be able to graph rational functions. This is advanced connect the dots. You know how when you graph functions, you put 2 or 3 or 4 or 5 and then you boop, 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 connect the dots? Rational functions is advanced connect the dots. To make advanced connect the dots a little bit easier, we have this method for graphing rational functions called the Rady method. The Rady method will lead you through finding all of the pieces of information you need to play advanced connect the dots. Okay? The Rady method has to get started in factored form. So the very first thing you're going to do is you're actually going to factor the polynomial so that you can decide which of the values in the denominators are wholes if necessary. So we factor, unless it's already factored. That would be nice if it's already factored. Then once it's set up, we look for the roots. That's what R stands for, is root. Now we know that the roots are the same thing as the zeros. So all I need is any values out of the numerator. Those values will be my zeros or be my roots. You're going to plot these points on the x-axis because they're x-intercepts, roots, zeros, solutions. Your graph must cross through the root and cannot cross the x-axis anywhere else. Don't invent roots where they are not. The next step is to find the asymptotes. This is the A of Rady method. We're going to find specifically the vertical asymptotes. You're going to set that denominator, whatever's left, that's not a whole, equal to 0 and solve, because you're not allowed to use those numbers. These will be your vertical asymptotes. You will then go on your graph and you will graph dashed vertical lines every place a vertical asymptote would be. The T of the Rady method is going to be new to you. It's called tangency and togetherness. It's tangency of the roots. Basically, it's the multiplicity of the roots. If you look at all of the roots in the numerator and you have any sort of even multiplicity, then you know from what we've learned about polynomials that that is not going to cross through the x-axis there. It's going to touch and turn. It's going to be tangent to the x-axis at that point. So what you're going to do is you're going to write the word bounce next to any root that would bounce, because that's information for us to be able to graph. Tangency was multiplicity of values in the numerator. Togetherness is essentially multiplicity of values in the denominator. Togetherness about a vertical asymptote occurs when there is a factor with an even multiplicity in the denominator. So you're looking for those even multiplicities. This means that the limits on each side of that vertical asymptote will come together at that vertical asymptote. You are going to write the word together next to each vertical asymptote that has an even multiplicity. We need to add our end behavior as information onto this graph. End behavior is actually significantly easy if you know Bobo, Bot, and Betsy. So you will write the equation for Bobo and Betsy equations as a horizontal asymptote, draw a horizontal line. Or for Botten by 1, the slant asymptote, which we have to find with division. We're going to graph these horizontal or dash lines on the graph. The last thing we need is the y-intercept. The Rady method ends with the y-intercept. This one's also easy. Finding the y-intercept, just like with polynomials, means that we're plugging 0 into the function, gonna get out a value, and we will plot that on the y-axis. So Rady stands for roots, asymptotes, tangency and togetherness, end behavior, y-intercept. If we can find these things, we're going to be able to graph any rational function by playing advanced connect the dots. Advanced connect the dots. That's all it is. We're playing connect the dots. It's just advanced. Let's try one. We are going to be graphing the rational function 2x minus 1 divided by x minus 1. We always start by looking at the information in the Rady method. We'll start by factoring the polynomial if possible. This one is not factorable, so it has no factored form. Actually, technically it's already in factored form. And since nothing matches on top and bottom, there are no holes for this graph. You get to fast forward through that step. Yay. Let's do the R. The R is finding the roots. The roots come from the numerator. So what I'm going to do is I'm going to take the equation in the numerator, 2x minus 1. I'm going to set it equal to 0, and I'm going to solve. How would I solve this? What's the first step? Move the 1. Now it's 2x equal to 1. What's the next step? Divide by 2. So x is going to be equal to positive 1 over 2. Immediately, we're going to graph this root on the x-axis. So we go to our graph. We find where x is equal to 1/2, which is approximately here. Do your best. Halfway between 0 and 1 is a half. And we put a dot on our x-axis. That's blue. We go to the A step. The A step is the asymptotes. Asymptotes come from the denominator. So we're going to take the equation in the denominator, set it equal to 0, and solve. What would I do to solve this? Move the 1. Basically, I'm finding the number that I cannot plug into the denominator. What number can I not plug into the denominator? 1. So x is not allowed to be equal to this number. We're going to take an orange marker or orange something or an orange whatever color code you made, asymptotes, and you are going to draw a dashed line down the graph at 1. We are not allowed to touch or cross that line. At x equal to 1. Yeah, so it should like cross or karate chop the x-axis at 1. It's kind of hard to see. Let me try to use a highlighter. That's the wrong color. Okay, we've got good info going on. We go to the T. The tangency and togetherness is looking at whether there are any squares on factors in the top or squares on factor in the denominator. Are there any squares at all in this problem? No. So there is no tangency, no togetherness. We are not going to bounce on any of the roots, and we're not going to come together on any of the vertical asymptotes. We go to the E. The E stands for end behavior. End behavior is Bobo, Bot, and Betsy. So if we look, what is the degree of the numerator? What's the degree of the denominator? 1. So is this Bobo, Bot, or Betsy? It's Betsy. And so we need to divide the coefficients. What's the coefficient of the top? 2. And what's the coefficient of the bottom? 1. So 2 over 1 is 2. So we go back to our graph. Every time you answer radi something, you can go graph it. And we're going to draw a horizontal line at y equal to 2. I know that's kind of hard to see, so let me add some backup lines. You are not allowed to cross this line at the ends of the graph. You can technically cross the horizontal asymptote in the middle of the graph because horizontal asymptotes tell us end behavior. At the end, no touching or crossing this line. In the middle, you technically can. Last thing we need is the y-intercept. The y-intercept is pretty easy because it tells me just to plug 0 into the function. So I'm going back to the function written on the paper, and I'm going to do 2 times 0 minus 1 over 0 minus 1. What's 2 times 0? 0 minus 1. Okay, and then 0 minus 1? Yeah, so negative 1 over negative 1 gives me 1. We are going to have our y-intercept at 1, which means I come over to my graph and I plot the y-intercept at 1. Here's why this is now advanced connect the dots, because this is technically enough information for us to graph the function. Here's the things I know. I know that I have to cross these two lines. I have to touch this and I have to cross through this. I know I'm not allowed to cross this vertical asymptote, no touching. And I know that at the ends of the graph, I need to be getting close to this yellow line, my horizontal asymptote. This is where it gets hard. My best advice is to start where the most information is. Where's the most information? In the middle, right? We know we have to connect these two together. So if I go to connect them, okay, boom, I've connected them. It's going like this, right? If I keep going, am I allowed to cross that orange line? No. So it's going to go very close, but just go straight down. I had to connect these two, which means it has to keep going down. Okay, now question, can I work the other way? If I connected from blue to green, am I allowed to cross this yellow line towards the end? No. So really, I'm going to say I should be stuck underneath that yellow line because that's my horizontal asymptote. Getting close to, but never crossing the end behavior line.
How do you know if it's in the middle?
What do you mean?
Like, you said you can cross the thing in the middle.
In the middle, it would be like if your y-intercept was here.
So that means it goes down underneath.
Yeah, it behaves differently sometimes in the middle, and you can cross it, but at the ends, once you run out of middle points, no more crossing.
Okay.
No more crossing. Now, my question, we've got like one of the branches here. I need to graph some stuff over here. This is where togetherness at the vertical asymptote comes into play. Did we have any togetherness?
No.
No. So by togetherness, I mean these arrows would not be going the same direction. They would be going opposite directions. So I need my other arrow on the other side of the vertical asymptote to appear up here. Then I scoop out and I get close to that end behavior line on the other side. No crossing, no touching. That is the rational function. Finding the radi stuff is easier. I mean, it's not easy, it's easier. Actually plotting the graph, kind of hard. Can we try another one before you ask major questions? Because I think seeing it twice would be helpful. Okay, let's look at this guy. Oh, look, it's already factored. Hooray, we didn't have to do the factoring. You may have to factor later, but today, for this one, we didn't have to factor. So it's already in factored form. Are there any of the same factors on the top and on the bottom? Like you would see like x plus 2 on both top and bottom. No. So there are no holes in this graph either. Nice. We start with the radi method. The R in the radi method stands for the roots. Roots come from the numerator. We're going to put whatever is in the numerator down on our paper, set it equal to 0, and solve. How do I solve for x here? I just square root it. And what's the square root of 0? 0. So this is x equal to 0. That is the only root for this particular rational function. So I go to my x-axis and I draw my x-intercept. Boom. For the A, that is the asymptotes, we are going to take the stuff in the denominator, which is x plus 2, set it equal to 0, and x minus 4 squared, set it equal to 0. I didn't write down the square on purpose because we're just finding the 0. So what are the two numbers that would give me vertical asymptotes? 4 and negative 2. So we are not allowed to be these numbers. So I go to my graph and I'm going to plot two vertical asymptotes. I'm going to plot a vertical asymptote at negative 2 and I'm going to plot a vertical asymptote at 4. For me, this is orange. So here comes the orange one at 4. No touching, no crossing that one. Here's negative 2. No touching, no crossing that one. Negative 2, yes. Now we do the T. The T stands for tangency or togetherness. Are there any squareds in the numerator? X squared, right? Interesting. So we are going to have a bounce. It's going to touch and turn at that value x equal to 0 because of the square on that factor. Are there any squares in the denominator? Really?
Oh, wait, I didn't see
that x minus 4 is squared, right? Which means we are going to have togetherness at the vertical asymptote, x is not equal to 4. We're going to have a bounce at 0 because it's squared. We're going to have togetherness at the vertical asymptote at 4 because of the square. So what I do on my graph to make sure I get this right is I'm going to literally write the word bounce next to that 0. So I remember, like, hey, no crossing. We're going to bounce on that one. And I'm going to write the word together on the vertical asymptote at 4. They should go the same direction there.
Why is it bounce at 0?
Because the x is squared, so it's a repeated root at 0, multiplicity 2. Even multiplicity is touch and turn. Okay, now we go to the E. E is for end behavior. Is this one Bobo, Botner, Betsy? How many zeros would be in the numerator?
2.
How many would be in the denominator? 3. Ooh, why 3? The square
Plus the x.
and then the other one.
Yeah.
So that's 3. So this is 2 on top, 3 on bottom. This is a Bobo equation. Bobo equations will have horizontal asymptotes at what number? Y equals 0. So we're going to go in with our highlighter that we're using for end behavior. For me, it's yellow. And we're going to draw a dashed line at 0. Here's what I mean by you can technically touch or cross it in the middle. Because, like, our 0 is on 0. And it's on the line we just drew. So it's okay to touch or bother the horizontal asymptote in the middle. But at the end of this graph, no touching. End behavior, not middle behavior. We need one more piece of information to be able to graph this. We need the y-intercept. So we go do the y-intercept. All that means is we're going to plug 0 into the function. This is going to be 0 squared over 0 plus 2 over 0 minus 4 squared. Now, that's a lot more work than I really want to do. What do you notice about the numerator? So if a numerator is 0, that means the whole thing is 0. If a denominator is 0, that's broken, that's undefined. But if a numerator is 0, it's 0. And our denominator would not be 0. So we know that we have a y-intercept at 0. And this makes sense because we've literally already plotted that here. When you're stuck in these kinds of problems, on the connect the dots aspect of it, and your book does this for every problem that it does, which is a really great method, if you need more information, because you're like, I still don't know what to do, Miss Quigley. There's a lot of things on my graph, but I don't know where to start. What you can do is you can plug in just another value that's near some things that are interesting. For us, we have interesting things happening here, because we have a y-intercept and an x-intercept and then a vertical asymptote. Why don't we choose one of these numbers and let's plug it in? What number of this would you like to plug in?
3.
Sure, let's plug in 3. Because if we get x equal to 3, what we're going to do is we're going to plug the number 3 into the function. This would be 3 squared over 3 plus 2 times 3 minus 4 squared. We're just getting another input-output. So this is 9 over 5 minus 1 squared. What's negative 1 squared? Negative 1 times negative 1? Positive 1. So we have 9 over 5 times positive 1. That ends up just being 9/5. Kind of gross to graph this, but we can. If we go to 3, we should go to 9/5, which is somewhere like here-ish. Do your best. This now gives me enough information to graph the function. Generally, need 2 coordinate points. And since my x-intercept and my y-intercept were the same point, it's not helpful. We needed 1 more point. Or anytime you're stuck, plot a few more points. It's clear to me that I need to connect these 2 together, right? Because it has to go this way. So I'm going to go ahead and connect those together. And then I'm like, ooh, a vertical asymptote. I'm going to get close, but I'm never going to touch. Now, around that vertical asymptote, you wrote the word together. So should I put the next arrow on this side or on this side? Top or bottom? Top, because we said together. So that's going to go the same direction. They're going together. And then I'm going to graph this down. I'm like, oop, horizontal asymptote. Let me scoot out to the side. If we start working the other way, can I cross through this x-axis? No, what did we write down next to it? Bounce. So that means this is not going to go through to the negative numbers. It's going to bounce back up and have to skirt up next to that vertical asymptote. Did we write the word together on this vertical asymptote? No. So should the arrow be on top or the arrow be on bottom? Bottom. Because it cannot go together. That was not the vertical asymptote that had togetherness. You're then going to take your arrow up and towards the end behavior without crossing or touching that line. See what I mean by advanced connect the dots? This is totally a lesson to do in pencil. Don't use a pen when you're doing these. We've done 2 examples so far. We're going to do 1 more together as a class, but does anybody have a question that they want to ask before we try 1 more? That was stretching. Okay. Yes.
About the togetherness.
Yes. Just in general? So in this one up here, there was no squares. So there's no tangency, no togetherness. Every x-intercept should cross through, and every vertical asymptote should be opposite. On this one, because there's a square in the numerator and a square in the denominator, there will be tangency at that x, so a bounce, and togetherness at the vertical asymptote that had the square. This is the one that has the square, so that's the one with togetherness. Togetherness means the arrows need to go the same direction. Since when we were graphing it, this arrow went up, right on the other side of the vertical asymptote should also be going up because we wrote together next to that vertical asymptote. The other one, we did not write the word together, so we cannot put the arrow here. The arrow has to be at the bottom. So it tells me how the graph behaves on the very left side of the graph. Great question. Other questions? Yes?
So if the balance at x equals 0, if that was like 3x squared, would it be the balance at 3x? Or would it still just be at 0?
Well, you would still solve. So if it said 3x squared equal to 0, when you're solving for x, you divide by 3 first.
Oh, yeah.
What's 0 divided by 3?
0.
Still 0. So that one would still be at 0. If it said x minus 3 squared, that would be a bounce at 3. Can we try another? Fabulous. Oh no. Is this one factored? No. So what do we have to do? Factor it first. We need to know what the factored form of this this rational function is. But we know how to factor. What are the numbers that multiply to 18 and add to negative 9? 6 and 3. Let's make them both negative. Very nice. Then for the denominator, we're looking for numbers that multiply to negative 12 and add to 4.
Multiply to what?
Negative 12.
6 and 2. Negative 6. No, 6 and negative 2.
Those would work, but they don't add to 1.
Oh, you can't. No, you can't.
What's another factor of 12?
1.
4 and 3.
4 and 3. Let's make it positive 4 and negative 3. We factored it. What's the same on the top and bottom? The x minus 3, yes? So I'm going to say that x minus 3 is going to create a hole in my graph. Not a vertical asymptote, not a 0. It's a hole. So on this first step, we actually are going to have a hole here. So we're going to have a hole at x equal to 3. Now, to find out where we put the hole in the graph, you are going to plug the number 3 into the function without the crossed out factors in it. Meaning, you're going to plug it into 3 minus 6 over 3 plus 4. 3 minus 6 is negative 3. 3 plus 4 is 7. So I have a hole at the coordinate point 3 comma negative 3 over 7. That gives me the first plot on my graph. When you go to plot a hole at the coordinate point 3 comma negative 3 sevenths, you're literally going to put an open hole right there. Just do your best on the negative 3 sevenths. It's a very small value. Just make sure there's a hole there. Then we start the Rady method. What does the R stand for in Rady method? Roots. Roots come from the numerator, and it only come from the stuff in the numerator that's left over. What's the only thing left over in my numerator after I cancel stuff out? X minus 6. So what is x going to be equal to? 6. Nice. That gives me my second point, since we had a hole, at 6. We're going to go over there with our blue or whatever you're using for the roots, the zeros, the x-intercepts, and you're going to plot a hole or a point at 6. Nice. The asymptotes of the graph appear from values in the denominator after we cancel out factors. So what's the only thing left in the denominator after we've canceled out all the stuff? X plus 4. So what number is x not allowed to be equal to? Negative 4. So we're going to go back to our graph. And we're going to plot that vertical asymptote at negative 4. I use orange, if you're following my color scheme. Are there any squares for the t-step? Are there any squares in the numerator after, we factored it, right? Any squared factors in the numerator or denominator? No, so there is none here. No tangency, no togetherness. The E is going to stand for end behavior. End behavior, we look at the regular unfactored form. This is where it's easier. Is this Bobo, Botner, Betsy? Betsy, which means we're going to divide the coefficients to find our horizontal asymptote. This is going to have a horizontal asymptote at y equal to 1 over 1, which is 1. We come back to our graph, we go to 1, and we graph our end behavior. Sorry, I went fast. We have one thing left to do. What does the y stand for in the Rady method? Which intercept? The y-intercept. The y-intercept is found simply by plugging in 0 to the function. You can choose to plug this into the regular version or the fully factored form. I like plugging it into standard form if you have it, because if you notice, if you plug in 0 here and you plug in 0 here, what's going to happen to these two terms? They're at 0. So what is the only number left in the numerator? What's the only number left in the denominator? When you plug in 0, all those x's cancel out from standard form. That's a little cheat code. Ooh, 18 over negative 12. That's going to reduce down to what fraction? 3 over 2. So negative 3 over 2. That is my y-intercept. So negative 1.5. So we're going to go to our graph. We're going to plot negative 1.5. And we're going to play connect the dots. Remember, advanced connect the dots. You're going to try to go where the most information is. Where is the most information? In the middle-ish, yes? I need to connect the y-intercept to the gap at the hole and the gap at the hole to the 0. So for this one, we didn't need a piece of information because it's clear how to connect those two things together. If I'm going like this, can I cross that yellow line at the end of my graph? No, so I'm going to skim outwards that way. As I'm coming down back through the y-intercept, am I allowed to cross the orange line? No, so I let it skim down to the bottom. Do I have tangency at this vertical asymptote? No, so should the arrow be at the bottom or at the top? The top. So I go to the opposite side of that vertical asymptote, and then I draw the rest of my graph. Ooh, that was not a very steady line. We get close to, but never touch, that horizontal asymptote.